Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Inferential Statistics. Part 4. Estimation of population proportion.
In this session, we will be looking at estimating what I would consider the most common parameter of a population that people normally estimate, which is the proportion of a population. This has a very wide range of applications. The Gallup poll, most of the TV or magazines polls are using estimation of population proportion. Population proportion is about a percent or a proportion of people in the population perhaps that have one opinion or the other. It deals with discrete variables. It deals with the yes or no, pass or fail, with or against. So you can see that that is very, very common. We'll show you in this session how we estimate that. In fact, if you understand what happens in this session, you will very much get a good idea about the people that actually estimate the election results in advance every 4 years, if we're talking about presidential election. And you will also see how different polls organizations operate and what parameters they are interested in. So let's go to the slides and see.
Perhaps the best way to start our discussion of how to estimate population proportion is to take a simple example, like having a mountain or a big container of candies, as you can see here, of different colors, and we are interested in the candies of the blue color, for example. So in this case, we will take a small sample from this very large population and count the blue candies in this sample and look at their proportion in the sample as a way to estimate the proportion of the blue candies in the population. So here is our population, and we take a sample from this population, say of 500 candies, and we count the number of blue candies in the population, and suppose we found that the number of blue candies is only 120. So that means we can calculate the proportion of blue candies in the sample. That is by dividing the 120 over the 500. So 120 over 500 is giving us 0.24, or we can say that the proportion of blue candies in the population of different colored candies is 0.24, or about 24% of the candies are blue. This is what we call a point estimate. Obviously, if we take another sample, we may not exactly get 120. But for right now, we need to understand that the proportion of the blue candies in the sample is what we call it the point estimate, or the expected value, and that's what the symbol E means, the expected value of the proportion of the blue candies in the entire population. And that is what we will have to symbolize it by a P hat. So a P hat normally indicates the proportion in the sample. If we take another sample here, as you can see, we find that the proportion is different. even if we take the sample size of 500. Now we have 100 blue candies, given a new proportion of 100 divided by 500 or 0.2. So in the first sample, we had 0.24 or 24%. In this sample, we have 0.2 or 20% of the blue candies. And that is what we meant early on by the sampling variability. And that is why we normally have to construct a sampling distribution of proportion. As a result of all of that, we need a confidence interval. We need an estimate, an interval estimate. And we need confidence associated with this interval estimate. And the general form of the interval estimate is very similar to what we discussed before. P here is the proportion of the blue candies in the entire population. P hat is the proportion of the blue candies in the sample, or the point estimate. And as we mentioned before, the point estimate has to be associated with interval estimate, and that is represented by plus or minus E, or plus or minus the margin of error. So now we can say that the proportion of blue candy in the population will range from P hat minus E to P hat plus E, and that will be our interval estimate. But we still need a confidence. So here is the formula. P will be from P hat minus E to P hat plus E, which is very similar to this one, it's just a different mathematical format. If we're talking about two-sided confidence interval, meaning from 2, we can easily use this formula here to express our confidence interval. This is P. This is the population proportion. This is P hat. This is the population, this is the sample estimate of proportion. So P is the population proportion, P hat is the sample proportion, and as you can see here, P is estimated by P hat minus the margin of error consisting of the Z value, we all familiar with this now, times the standard deviation of proportion, and the upper value is the P hat plus the margin of error consisting of the Z value times the standard deviation of proportion, or the standard error. So P equal to P hat plus or minus Z times sigma P. Now, we defined sigma P in the previous chapter as the square root of the proportion, the estimate of the proportion, times 1 minus P hat divided by N. So we basically know everything. We will know from the sample the P hat, we know the sample size, and all what we have to do is to calculate the Z value to be able to complete our estimation. I also need to point out that if we are dealing with one-sided confidence interval, meaning the proportion of blue candies being less than a certain value or greater than a certain value, then we will use these inequalities to do the estimation. Meaning P hat minus the margin of error less than the population proportion, or the population proportion being less than the P hat plus the margin of error. Also, if you recall, we needed to estimate the minimum sample size required to be able to estimate the mean value of the population. Likewise, we can estimate the minimum sample size required to estimate the population proportion. Here are the formulas that I just presented for you for double-sided. And if you notice here, N, or the sample size, is presented in the margin of error. or the standard error associated with the estimation. So how big this sample size n should be, or how small it should be, in order to estimate the population proportion accurately. Now the equation to determine the minimum sample size is as follows. N equal p hat times 1 minus p hat times z over e square. Now notice the problem here is, in order to calculate p hat, we need n, we need the sample size, because p hat is equal to the number of items of interest x divided by the sample size. So how in the world we're going to be able to calculate the minimum sample size n from p hat if p hat itself requires a sample size n? We're going to see this by example, and we're going to see how we go about that by example shortly. We know that P, or the proportion population, is estimated from P hat plus or minus this value here, or the margin of error, which we called it before E. So in order to calculate the percent margin of error, we need to divide E by the P hat times 100. So if you ever want to calculate the margin of error in percentage, it is E, or this entire value here, divided by P, the point estimate, times 100. Now let us take an example to summarize all these rules in an application. According to a New York Times CBS News poll conducted during June 24 to 28, 2011, 55% of American adults polled said that owning a home is a very important part of the American dream. Now, since we are talking about a poll, then what we have is a sample proportion. Polling is sampling from a large population. So this is a p hat. This is the proportion of a sample, 55% or 0.55. This poll was based on a sample size of 979 American adults. So now we have p hat, and we also have the sample size n. And we have basically three questions here. Number one, what is the point estimate of the population proportion? Number two, find with a 99% and a 95% confidence level the percentage of all American adults who will say that owning a home is a very important part of the American dream. Finally, what is the margin of error of this estimate at 95%? Let's see how we go about solving this problem. We'll start out with the givens, and the givens are the sample size n, 979, the p hat, or the proportion of the poll or the sample, 55% or 0.55, which means that the complementary proportion is 1 minus p hat or q hat equal 0.45. And what you see here is a condition that should be satisfied in our estimates all the time. That is n times p, and the n times q should always be both greater than 5 in order to validate our estimation, as I will explain later on. So the first step is we need to calculate the standard error, which is part of the interval estimate. It's equal to p hat q hat divided by n, or the square root of 0.55 times 0.45 divided by n, which is 979, and that gives us 0.016. Now, The point estimate, as we know, is 0.55. But the interval estimate has to be calculated as at a confidence level of 99%. And what we need out of that is a z-value. And we know that at 99%, the z-value is 2.58. So here is our expression of interval estimates. P, or the population proportion, is estimated by p hat, or the sample proportion, plus or minus z times the standard error, or s p hat, or the standard deviation or proportion. So that gives us p hat, which is 0.55, plus or minus the 2.58, which is the z-value at confidence level of 99%, times the standard error, which we calculated earlier, and that gives us an 0.55 plus or minus 0.041. Which means if we subtract this 0.041 from 0.55, that will give us the lower value, 50.9%, or 0.509. And if we add this margin of error 0.041 to 0.55, that will give us 0.591, or 59.1%. And what does that mean? It means we are confident in 99% that there is a ratio or a percent from 50.9% to 59.1% of Americans that will say that owning a home is part of the American dream. Now, if we try to do the same estimation at a 95%, let's see what's going to happen. Here again, we have the standard error as we calculated it before. We have a point estimate of 0.55. At 95%, z is 1.96. And if we substitute that in our expression of interval estimate, we're going to get a new margin of error. 0.55 is a point estimate, but this time it's plus or minus 0.031. Meaning that at 95%, we are confident that the proportion of 0.519 to 0.581, or 51.9% to 58.1% of Americans would agree that owning a home is part of the American dream. Let's compare these two estimations here. Here is the estimation at 95%, and here is the estimation at 99%. And this is very important here to compare the two, because the only difference between the two, keep in mind, in both estimates, we have the same point estimate of 0.55. We have the same standard error of 0.158. Nothing changed, the same sample size, and the same p hat and the same q hat. So the only difference was the z-value. In the first case, it was 1.96 because we were confident 95%. In the second case, it is 2.58 because we were confident 99%. And as you can see, the difference here is when we are more confident, when we have a higher level of confidence, you can see that the range of the interval estimate becomes wider. This is from 50.9 to 59.1, while at the 95% it was 51.9 to 58.1, meaning at 95% we have a narrower estimate than at 99%. The next question is we need to find the margin of error. And if you look at here, this is the margin of error at 95%, the plus or minus value. If you look at 99%, this is the margin of error. So basically, if we take at 95%, then the margin of error is going to be the 0.031. But if we need the percent, you see, this is the absolute margin of error. But if we need the percent of the margin of error, we have to use the equation that I presented to you earlier, which is E, that is the absolute margin of error, divided by the point estimate the p hat times 100. And when we do this simple calculation, 0.031, the absolute margin of error, divided by the point estimate 0.55 times 100, that gives us about 5.6% margin of error. So please distinguish between the absolute margin of error, this value as it comes in the estimation, and this value here, which is calculated from dividing the absolute margin of error by the point estimate times 100. Let's take another example. The article, How Well Are US Colleges Run? USA Today, February 17, 2010, describes a survey of 1,031 adult Americans. The survey was carried out by the National Center of Public Policy, and the sample was selected in a way that makes it reasonable to regard the sample as a representative of adult Americans. Of those that were surveyed, 567 adult Americans indicated that they believe a college education is essential for success. And the question here is, what is the 95% confidence interval for the population proportion of adult Americans who believe that a college education is essential for success? Obviously, the point estimate is very simple. It is the number of adults that said that college education is essential for success, which is 567, divided by the total number of adults being surveyed. So 567 divided by 1,031, that gives us 0.55. So we have a percentage of 55% of adult Americans who believe that a college education is essential for success. Obviously, there is another 45% that do not believe that college education is essential for success, as this sample indicates. Now, in order to estimate the population proportion, we use what we did a minute ago. Here is the expression for estimation. P, or the population proportion, equal p hat, which we just calculated, times the z critical value, times the standard error, p hat times 1 minus p hat divided by n. We have all this information. We know that at 95% z is 1.96, so the p estimate is 0.55, z is 1.96, p is 0.55, 1 minus p is 0.45, n is 1,031, and that gives us a range from 0.521 to 0.579, or 52% to about 58% of adult Americans believe that education or college education is essential for success. And we are confident in this estimate by 95% level. Or we are confident that if you keep doing these polls, that in 95% of the time, you're going to get a range from 52.1% to 57.9%. It's very, very important that you draw a conclusion. The idea of this problem is not just to do the calculations, but rather to actually draw the conclusion based on the analysis, the simple analysis that you perform. Another example. In a poll of 1,500 randomly selected people in the USA, 44% said that they take vitamins and the other dietary supplements on regular basis. So that's a sample, 1,500 randomly selected people. And 44% of this sample, or the p hat, or the point estimate, said that they actually take these vitamins. And the question is about estimating the population proportion of US adults that take vitamins and the other dietary supplements on regular basis at 95% confidence. We also have to pay attention to the next question. What is the standard error for the estimate of the proportion of all population in the USA that take vitamins and the other dietary supplements on regular basis? Once again, we have the point estimate 0.44. We have the sample size 1500, which means we can calculate SP, or the standard error, which is part of the question, as p hat times 1 minus p hat divided by n, or 0.44 times 1 minus 0.44 divided by 1500, and the square root of that will give us the standard error, 0.0128. We need the standard error anyway to be able to do the interval estimate. So at 95%, we have a z-value of 1.96, and here is the expression for the estimation. The lower level of the estimation is p hat minus z times the standard error, and the upper level is p hat plus z times the standard error. And we have all the values. We have the p hat being 0.44, we have the z being 1.96 at 95% confidence interval or confidence level. We have the p hat 0.44 times 1 minus p hat divided by the sample size of 1500, and that gives us the interval estimate from 0.415 to 0.465. And what is that tells us? That with a 95% confidence, that is the conclusion that you have to draw, we can estimate that on average the proportion of all people in the USA that take vitamins and the other dietary supplements on regular basis is 0.44, but it may range from 0.415 to 0.465, or 41.5% to 46.5%. Another example, a large company surveyed a representative random sample of 200 people of its employees regarding the addition of extended dental insurance. The result of this survey revealed that 160 of the employees prefer the new dental plan. So we have surveyed 200 people, as you can see here, and 160 of them agreed to the dental plan. And the question is, estimate the company population proportion. We only took 200, but we now need to estimate the entire company population proportion of employees that will prefer the new dental plan at 95% confidence. And we're going to repeat everything we did before. It's a systematic process, systematic steps. Here is a sample size of 200. Here is the employees that agreed to the new dental plan of 160. That gives us a point estimate p hat of 160 divided by 200. So we have 0.8 point estimate, or 80% point estimate, or 80% are saying that we agree. Now we need an interval estimate. We know at 95% the z-value is 1.96. We simply use the expression of interval estimate, substitute all the values, and here we are getting a estimate of the proportion of people that would agree to the new dental plan from 0.745 to 0.855, or we are with a 95% confidence can estimate that on average the proportion of all employees in the company who will prefer the new dental plan is 0.8 or 80%, but it may range from 0.745 or 74.5% to 0.855 or 85.5%. Now, as a follow-up to the previous example, it was determined by the company employees union regulations that at least 70% of employees must agree to a change before it can be approved. Now suppose the union will base its approval of this new plan on this sample information. What do you think the union will decide? Would they agree to the extended dental insurance? If so, why? Now, we just made the estimates on the approval of the dental plan based on the sample, and it came out to be from 0.745 to 0.855. Now the union insists that it had to be at least 70%. Now as we can see from here that we have a lower level of the estimate that is above the 70%, being 75% almost. So apparently the union will tend to approve the plan because of the fact that our sample estimate provides us with a value higher than the minimum threshold. Here is another example that also represents a follow-up on the previous example. Suppose now that the union were a bit strict on accepting new health plans, and they insist that at least 87% of employees must agree to a change before it can be approved. Now, if we rely on this sample, if it is 87%, then we know that this outside this range here, outside our interval estimates. Why? Because it's from 74.5% to 85.5%. So as a result, we can tell from our estimate that the union may actually disapprove the plan. The question here is, what if we did this estimate at a 99% instead of 95% confidence? Would that affect the decision of the union? And I'm going to leave this up to the reader and the listener to this session to find the answer to this question. What if we change our estimation to a 99% estimation? Would that alter the decision of the union? Here is another example. A sample of 500 students in a large university was surveyed regarding the addition of classes in the weekends. The results of the survey revealed that 120 students agreed to attend weekend classes, establish a 99% confidence on the acceptance by students' population of these new classes. You can see we are repeating ourselves here. Indeed, we have N, we have the number of students agreed to the weekend classes, 120. If we divide the 120 by 500, that will give us 0.24. That means we have about 24% of the students agreed to the weekend classes. And this is by itself, although it's a point estimate, is very important, because that gives us an idea that if the university decides to open new weekend classes, about what percent of students will agree to take these classes. But we need a complete estimation, because this may cost us money. We're going to open new classes during the weekend. We're going to have new teachers. We may have new equipment and so on. So if we follow the estimation procedure we did before, at 99%, we have 2.58 z-value. We find that the range of proportion of students that would agree to do the weekend classes is from 0.191 to 0.289, meaning we have a range from 19.1% to 28.9%. And what's so important about this estimate is that if we're planning to do weekend classes, then we're going to have to plan based on that range, meaning the maximum should be about 28-29% of students taking classes in the weekend, and the minimum will be 19%. And we did not have to survey a large population of students. Only a small sample resulted in this very, very important conclusion that can result in a better and cost-effective planning to open weekend classes. In the previous example, calculate the maximum sampling error. And what is the sample size required to reduce this sampling error down to half of the margin of error? or the sampling error. I want you not to be confused between sampling error and the margin of error. They both mean basically the same thing. Now here is our estimate at 99%. It was 0.24 plus or minus 0.0493. Now if we want to calculate the sampling error, the current sampling error, we told you before that the maximum sampling error or the margin of error is simply calculated by dividing this absolute margin of error by the point to estimate, the 0.24 times 100. So we have 20.54% margin of error. That's huge. That is almost 21 margin of error, 21%. And keep in mind that this example is about whether the university will offer classes in the weekend or not. So not only that we have to care for the estimation we got at 99% confidence, but we also have to wonder whether the margin of error we obtain is too high or too low. Because ideally speaking, we need the lowest margin of error in our estimation. And our margin of error here, as you can see, is almost 21%. We need to reduce this to half. Now, at half of this margin of error, which is about 0.025, we can use the formula for determining the minimum sample size. And as you can see from this formula here, we have p hat given, we have z given at 99%, and we have a new e of 0.025. This is the half of the previous margin of error. But look at the sample size now. It is 1943. Now you need to keep in mind that the sample size associated with this estimate was only 500 students. But in order to reduce the large margin of error of 20.54% or 21% down to half, we really have to use a much larger sample, almost 4 times the sample size we've used. And if we do that, we will be able to reduce the margin of error down to half the previous value, from 21% almost to 10%. Now, the merits of the previous example is that early on we mentioned 3 basic criteria for estimation. That is, we have to calculate a point estimate. Secondly, we have to have an interval estimate from 2. Thirdly, we have to have a confidence level associated with that interval estimate, 90%, 95%, 99%. I might as well add another important criteria, which is we have to select a minimum sample size at an acceptable margin of error. That is a key criteria, because we may have a good point estimate, we may have a good interval estimate at high confidence, but all of this may be associated with a large margin of error, and that is unacceptable in estimating population parameters from sample statistics. Before I leave the issue of estimation of population proportion, I need to discuss with you the correction factor for finite population. In the above sections, estimation was made based on the assumption that the population is very large or infinite. When a sample size of n is withdrawn from a finite population of size n, we may have a deviation from all the calculations we did before. as a result of the change in the ratio between the sample size and the population size being now a finite population. In this case, we should make the following correction to the standard error of the sample means and proportions. If we are talking about the standard error for sample means, we have to multiply the previous formula for the standard error by this correction factor, which is the square root of the population size minus the sample size divided by n minus 1, or the population size minus 1. If we are talking about proportions, it is the same thing. We have to multiply the previous standard error that we calculated by the same correction factor, n minus n capital minus n small divided by n capital minus 1 square root. Let's take an example to demonstrate how the correction factor works. We have a sample size of 100 drawn from two populations. The first population is very finite, 200, and the second population is 1000. Let's calculate the correction factor for each population to see how the correction factor works in the estimation. For the first population, where we have a population size of 200 and the sample size of 100, if we substitute the n capital and the n small in this correction factor, that gives us 0.709. That means we're going to have to multiply the standard error we calculated earlier by an 0.709, which means reducing that sampling error. But if we take a sample of the same size, 100, but from a larger population of 1000, we can see that as the population size increases, the correction factor approaches 1. That's 0.949. That's why we say that the larger the population, or the more infinite the population is, there will be no need to do any correction for the estimation of population mean or population proportion. Another example. In a small town of only 600 people, a survey was made using a random sample of 200 people regarding annexing the town to an adjacent city. 80 people agreed to the annexation action. Estimate the population proportion that would agree to the annexation at 95% confidence. Systematic analysis, we have the sample size 200, we have the people that agree are 80, that gives us a ratio of 0.4, or a proportion of 0.4, that's the point estimate. And at 95% we have a z-value of 196. But here, because of the finite population and the fact that we're taking a sample size of 200 versus 600 population, it may be useful to use the correction factor. If I use the correction factor in this estimation, meaning here is our new sigma p, the normal standard error, p hat times 1 minus p hat divided by n times the correction factor. In this case, our correction factor happened to be 0.817. That gives us a more accurate standard error. I can use that in my estimation, and I can follow the same procedure and make a more accurate conclusion, simply because I have considered the correction factor in my estimation.
The key issue here is that as simple as this application is, and as I said earlier, it really represents a very, very common type of estimation analysis in the real world. Every 4 years, as I said, we have over 100 million eligible voters. Yet we take small samples of 1,600 out of that, and that 1,600 have to tell us which candidate that they're going to vote for. That's one of the application of proportion, because we need to look at the proportion that goes for one candidate versus the proportion that goes to the other candidate. Surveying products, whether people prefer the existing product, the existing soda drink, for example, versus a new one that's introduced to the market. All these issues of pass, fail, yes, no, accepted, unaccepted, with, against, all of these deal with proportion. And you can see here that we have assumed normality. Because of that, we've used the Z statistic. And the reason for that is that we normally deal with a large sample to survey from. 1,600 people, 500 machines to select which machine that's functioning right, or what proportion of machines. College student sample, 200, 300 students to see which one passed and which one failed, for example. So since we normally in these applications deal with larger samples, then the use of the Z, or the use of normal approximation, is a very reasonable assumption, and that's why we've used the Z approximation, and we found the Z statistic for this type of estimation. In this session, we will go over how to use Excel spreadsheet in performing estimation or inferential statistics dealing with one parameter, which is the population mean value. So let's go to the slides and see how we do that. Let's take an example here. Here is a number of students, and we have about 20 students, and these are the students' ages. And we would like to establish a 95% or a 99% confidence on this, on the population of students' ages. And we learned how to do that in our previous session, since this is a small sample. And we now are about to use Excel to do that. Well, the easy way to use Excel to do this type of analysis is to do something that we are now familiar with, which is descriptive statistics. We can go to data analysis as we did in the past, and we go to descriptive statistics. And in descriptive statistics, we will go to the menu that we are familiar with. The first one is input range, which is this column here, given, of course, the labels. So we'll have to be from this cell all the way to this cell. That's our input range. We already know how to do that. And we'll specify an output in the spreadsheet to put our output in it. And in the past, we did summary statistics. This time, we're going to mark or check this box as well. This box says confidence levels for mean. And this value by default is 95%. So if we wish to do a 95% confidence, we can use this. Or if we want to change that to 99% or 98%, we can change it to any confidence level that we want, depending on what confidence we would like to establish for this estimation. And if we do that, we will get this type of output. Now, this output, again, should look very familiar to you. It has the mean value, it has the standard error, the median, the mode, everything we had before, but it has one added portion here, which is the confidence level at 95%. And as you can see here, this is 1.042. Well, what is this? This is basically the margin of error. This is the E term that we introduced early. So now I have the point estimate, which is the mean, and I also have an interval estimate, Why? Because I have E, right? If you recall this equation, and of course we only have 20, that's the sample size here, so Excel is smart enough to go and use the T statistic instead of the Z, all right? And the E value, or the X bar plus or minus, it's that value here, the 1.042 that we see here. So if you're going to use Excel to perform inferential statistics to estimate the population mean from a sample information, you have to keep in mind that this value here is the margin of error. And it will always be useful that you write this equation and you get this value here and put it in there, and by doing so you can actually estimate the lower range or the lower value and the upper value at 95%. So it's very simple. As you can see here, what we did, we went to descriptive statistics, and all what we did this time is we added confidence level. We could have done 95%, 99%, and press OK, and that gives us a descriptive statistics display that we are familiar with. The only difference here is we have the confidence level at whatever the level we specified, and this value here, as I said, is your margin of error, and that completes your estimation, because now you have the point estimate 20.7 plus or minus the confidence value, or 1.042, and this is all done at 95% by our specifications on Excel. Another way to do that, instead of using data, we can also go straight with the statistics we have. If we go to function in Excel and we go to statistics, or statistical as we did before, and then we select confidence. Now keep in mind, this time we're going to function X, then we select the statistical, and we go to confidence. This time we have to be very careful, because when we press OK or go, we're going to get a menu that will look something like this. And in the menu we are required to put alpha. If the confidence is 95%, alpha would be 5% or 0.05. If the confidence is 99%, alpha would be 1% or 0.01, and so on. We are also required to put the standard deviation and then the sample size. The point I have to emphasize here is, as soon as you put the standard deviation here, then Excel, since you don't have data, Excel will assume that this is the standard deviation of the population, while in fact we got this standard deviation from the sample. If I go back in the slides, when we did the descriptive statistics, our standard deviation actually came from descriptive statistics of this data here. So the standard deviation that we obtained, which is the 2.227, was actually the standard deviation of the sample. So as a result, when we use data analysis, descriptive statistics, Excel used a small sample size of 20 because we gave it that, and it used the standard deviation of the sample, and it knows it's a standard deviation of a sample, so it uses the T statistics. When you use the function key, on the other hand, and use the statistical functions, and you go to confidence, Excel does not know that you have obtained this value of standard deviation here from a sample. It only assumed that it came from a population. So as a result, and going by the first condition, if you recall, variance is known, it uses the Z statistic instead of the T statistic. Anytime you know the variance of the population, you always use the Z statistic instead of the T statistic. Of course, Excel here assumes that the value here is the standard deviation of the population, and there is no other way around it. We cannot tell Excel that no, this is the sample, so it assumes it's the population standard deviation, and as a result it gives us a value of 0.97, not the 1.04 we got. The reason for that is that it used the Z score instead of the T value. So be aware that if you use the function X, that unless you have the standard deviation of the population, you may be getting smaller value of margin of error as a result of Excel using the Z statistics instead of the E statistic. This is a very important note here, this difference from the values obtained the error of 104. The reason for that, Excel assumes that the standard deviation given is that of the population, thus it uses Z automatically, not T. As you can see in this session, and very quickly, we were able to perform estimation or inferential statistics analysis using sample data. We know that if we have sample data, we go to descriptive statistics and data analysis and perform descriptive statistics, and the only thing we have to add is we check the box of confidence and they specify the confidence we need. We now know that if we want to use the function x, we have to be careful, because all what the function x asks us to do is to insert the standard deviation and the sample size as well as alpha. And since it always assumes the standard deviation to be the population standard deviation, my advice is do not use the function x option unless you have a standard deviation of the population given. If you do have that, then you go ahead, you don't need data, all what you need to do is to specify alpha, standard deviation, and the sample size. Excel is a very powerful tool, as you can see. However, understanding the underlying concepts of what we do will help us reading the outputs of Excel easily, and will help us accurately describe what we see, and it also helps us understanding the meaning of the values obtained from descriptive statistics or from whatever the analysis we do. Next session, we will move into a very important subject, which is what I call the second side of the coin of inferential statistics, and that is the test of hypothesis.